Now I'm starting to. Okay, so so I've decided that there's where the function's positive and negative. And this is going to be one of the tools that we use in all the tests to decide the behavior of a particular function. Okay, any questions about this? Now, I'm not looking at any derivatives. I'm just trying to characterize what this particular function will do. Okay, so just for practice, why don't you try, where is it 0, positive, and negative for this function? Okay, go ahead and try that. Okay, so let's do this. Let's take a look at this. So the first thing you do is you factor it, and so this factors nice and readily. And then what we want to do is we want to figure out where the critical values are. And so the critical values of this particular thing, and in a sense it's not really a critical value because the critical value is actually the number in the derivative that describes where the mins and maxes are, right? And so here all we're looking for are the values that if this were a derivative, what would be the critical value. So I'm really talking about a function, and I'm finding out where is the function 0, where is the function undefined. And so it's 0 at x equals 1 and x equals -1, and it's undefined when x equals -2. And so those are the three numbers that will be my kind of guideposts in making my 4 intervals, right? I have an interval both on the inside and the outside. So we start at -infinity, go to the lowest value, which is -2, and then we go from -2 to the next lowest value, which is -1. -1 to 1, and then 1 to infinity.
So we're just pretending this is...
Yeah, I'm just trying to characterize this function. Yeah. I'm trying to see where is f at x positive and negative. There's no ulterior motive here other than to find when is it positive and negative. Then we'll use this technique to decide on increasing, decreasing intervals and all that kind of stuff. We're going to do it with a derivative. But here I'm just trying to characterize the function. This is a particular thing that really we probably talked about first in maybe the second week of class, something like that. Okay, so what I'm interested in is what's the behavior of those 3 factors that are in there, and what's it going to do to my overall function. So when I'm anything below -1, x plus 1 is going to be negative. Anything above -1, it's positive. Okay, everybody follow that one? You can see where that's where that particular sign changes. Now the x minus 1 changes to positive at 1, right? Anything less than 1, like if you put 1/2 in there, you end up with -1/2. So you have one more negative interval there. And x plus 2 is going to be positive everywhere except where x is less than -2. Okay? So now we count up the positives and negative signs, and we find that we have the sign f at x is less than 0 when we're below -2, and it's less than 0 when we're between -1 and 1.
And that's the answer?
Yeah, that's the answer I'm looking for right now. It's just where is it positive and where is it negative. So this is kind of a prelude to the tests that we have. This will be the tool that we use when we say, okay, when is the derivative negative, or when is the second derivative negative? Okay, so we're going to take a little side track here and talk about this mean value theorem. Now this sounds an awful lot like the intermediate value theorem, right? What's the difference? Remember what the intermediate value theorem said, that if I have a point on a contiguous function, if I have 2 points and I pick a point in between, then I'm guaranteed to have an x value that gives me that value. So we use that in finding these zeros. You know, when we have a positive and we have a negative, we know it has to go through 0 with a continuous function. The mean value theorem has to do with derivatives. Now, I'll tell you the way I remember the difference between the mean value theorem and the intermediate value theorem, because the ordinary meaning of intermediate and mean, to me, you know, they're almost indistinguishable. So I was driving along the Pennsylvania Turnpike once, and I noticed I passed a state trooper, which is the Pennsylvania equivalent of a highway patrolman. He was parked just on the side of the road. And so I was doing the speed limit, and then when he was clear out of my sight, I sped up and I was going my usual 10 miles an hour over the speed limit. So I drove for a little while, and then I thought, maybe I should slow down. So I slowed down, and there was another trooper, and so I thought, oh, I'm glad I slowed down. And so I drove past him, and he pulled up behind me, turned the lights, and cited me for going faster than the speed limit. Now, how did they know that I was going faster than the speed limit? Okay, it's because of the mean value theorem. And I remember it's the mean value theorem because Pennsylvania state troopers, I think, are mean. Okay, so maybe this is my profile. Okay, so I started off at A, and I have a certain position, and then I'm driving to B, and that slope is just calculated from F at B minus F at A over B minus A. So in other words, I can calculate what my average speed is. So if that's a distance graph, the slope of that is my speed. Okay, so what the intermediate value theorem says is that there is some place along that curve, if that curve is continuous and differentiable, that there's some place along that curve where it has a derivative that's exactly that slope. So in other words, the Pennsylvania police officers knew that that at some point I was going faster than the speed limit because my average between those two was faster than the speed limit. Okay? So even though they didn't observe me faster than the speed limit, they knew my average was higher than that. And it's the mean value theorem, those mean Pennsylvania state troopers, that said that the slope of that graph somewhere has to be what the slope of the line that connects the 2 points are. Now, a little bit more formally stated, here's the mean value theorem. So, moral of the story is, don't take calculus or don't drive in Pennsylvania. I don't know, but anyway. So if f is differentiable on this interval, a to b, then there exists a number c such that the derivative at c, of f at c, is the slope of the line that connects the two endpoints. Now, contrast that with the intermediate value theorem. The intermediate value theorem says that in order for me to go from f at A to f at B, I'm going to have to cross some value c, where this is a different c now, where I'm going to have some intermediate value. In other words, I can't go from here to there without going through every point in between. That's the intermediate value theorem. The mean value theorem is that my average rate of change somewhere equals the rate of change that I would calculate from the average of the overall interval.
This is very specific.
Yes. Okay, so the intermediate value theorem we used for this stuff. This is, we know that the signs change because of the intermediate value theorem. To go from a negative to a positive, it has to go through a zero, and that's why we have these zeros as the places that we cross. That's the intermediate value theorem. What the mean value theorem will allow us to do is characterize the behavior of graphs based on the value of the derivatives. Okay, so there's a lot of uses for, and here I actually probably, I need to edit this. I put in intermediate value theorem because I was thinking mean value theorem, but it's, so I'll need to change my, my slide. So I'm going to cross it out just so if you're watching this that you don't get a mistaken notion. This is mean value theorem. Okay. So the consequence of this is that it leads to the increasing and decreasing test. That means that if the derivative of a function is positive over an interval, that means that f is increasing. Okay? And then the other part of that is that if the derivative is less than 0 on an interval, then f is decreasing at that point. And this was one of those things that we looked at the very, very first class, where we're looking at rates of change. And when something is going up, we have a positive derivative. When something's going down, we have a negative derivative. Okay, and this is saying that over an interval now, if the derivative remains positive, that means the function is increasing over that area. So it's stated a little differently, and this is stated in not quite ultra-formal kind of math, but it does rely on the mean value theorem and the fact that we're going to be looking at derivatives to characterize functions. Okay, so now here's a function, 3/4 x to the 4th minus x cubed minus 3x squared plus 2. Where does it increase and where does it decrease? All right, so what we're going to do here is we're going to look at the derivative of this thing and decide where is the derivative positive or negative. And lo and behold, if you've already calculated the derivative, you'll see that the derivative is that function that we did the very first exercise in class.
Oh,
okay?
and then we just do that and we find out.
I did this. So I didn't tell you it was the derivative of the example that I was going to use for this, but we've already done this analysis. Okay, so we've said that now I'm going to characterize this as the derivative. Okay, so I'm just going to change the notation here so I'm consistent with my example here. So if I take the derivative of f at x, all this stuff applies. My derivative now is, you know, factors to this nice 3x times x plus 1 times x minus 2. And so we know then, because the derivative is positive and negative, that over these intervals, our function is either increasing or decreasing. Okay, so we say f at x decreases with those two intervals, and then it increases with the other two. Okay, so this is something that you've done twice before already, at least, but it's stated with a little bit more formality, and we actually call this the increasing and decreasing test. Okay, so it involves looking at the nature of the derivative. Okay, so it's about 10 minutes till 9, and so I'm going to kind of blow through some of these examples. Ideally, I'd like you to do these, but I have them worked out. So let's just think about how you would do this. You would take the derivative of this thing,
Then do the test.
and then do the test. You would look at all the factors involved there, see where the derivative equals 0 to define where your intervals are, and then see what those intervals do. So if I take my derivative, and simplify it, I can remove a 4x and end up with this minus x plus 1 over x cubed. So I essentially have two factors. I have this minus x plus 1, and I have x cubed. So what I'm looking for is where does the derivative equal 0 for 1, and where does the derivative not exist? Okay, because where it doesn't exist, I have a potential for the sign changing. Remember in those toolkit functions, we had 1 over x that looks like this. Okay, so there's no derivative at x equals 0, but you know that the sign changes when we go from positive to negative because of this sort of thing. So we include that as one of the critical values that we're looking at. All right, so since we have two factors, we have three intervals up to 0, and then 0 to 1, and then over 1. And we look at our three factors, we characterize them, and decide what does the derivative do. And so now that we know what the derivative does from a sign standpoint, we know whether the function increases or decreases. So it increases from 0 to 1, and it decreases outside of those two intervals, or outside of that central interval. Okay? And so if I look at a graph of this function, this is kind of a truncated graph, but you can see, what it does, that we have, it's increasing from, 0 to this point here, which looks like it's about 1, and then it starts to decrease from there. So it tells us, below 0, it's also decreasing like that. Okay, so the second of our named tests is the first derivative test. And so the first derivative test is, suppose C is a critical number of a continuous function. Okay, so what we have is that if the derivative changes from positive to negative, then f has a local maximum. And if the derivative changes from negative to positive, that means we have a local minimum. Okay, so if I were to make a picture of this, if the derivative goes from positive, so that means it's increasing, to a derivative that's negative, that means it's decreasing, that means I have a local maximum there. Same thing if the function is decreasing, and then the derivative changes to a positive value and starts to increase, then I have a local minimum. And we call this the first derivative test. And actually, you've already done this. Okay, so if the derivative doesn't change its sign, then you have no local minimum or maximum. All right, so think about some functions where you have the derivative equals 0, but below that point the derivative is positive, and above that point the derivative is positive. Remember, we had a few of those. That means that that's not a local minimum or maximum. You knew that as one of these things that, well, in the next example I'll have a picture of how that works. Okay, so this is our first derivative test. Okay, so we want to find the local minimums and maximums with the first derivative test of this particular function. All right, so I'm going to take the derivative of this thing. And then I'm going to factor it. Now, if you tried to factor this one, factoring this x cubed minus 3x minus 2, you do that by trial and error with synthetic division or polynomial long division. And you know from the ratios of 1 and negative 2 that your candidates are going to be, a ratio of 1 and 2, or 2 and 1, or actually 2 and 1, either positive or negative. So you have some candidates, and it'll take some trial and error to factor this. But I chose this one because when you do factor it, I get something that will show me one of these critical points that doesn't end up with a local minimum or maximum. So in a sense, this is kind of a contrived problem just to get to this point where I can show you that at a critical value you have neither a positive or a minimum or a maximum. So once I factor my derivative, I look at where my zeros are, and I'm going to have a 0 at 0, 2, and negative 1. So I'll put those in order and make my intervals like I did before. And then I'll take my 3 factors. And here with the squared, I can keep that just as one factor, right? There's no point in making that 2 factors because those will always agree in sign, so they'll always be positive. So when I fill out my chart of negatives and positives, when I'm negative, x is going to be negative. When I'm positive, x is going to be positive. Then with the x minus 2, I'm going to be negative until I cross 2. And then with x plus 1 squared, I'm always going to be positive because I square it. And so my derivative then tells me that I'm going to have a positive derivative over those first 2 intervals. I'm going to have a negative derivative over that 0 to 2 interval, and I'm going to have the derivative is going to be positive from 2 to infinity. So what this says then is that since I'm flipping from positive to negative, I have a local max at x equals 0, and I'm flipping from negative to positive, at x equals 2, that means I have a local minimum. Okay, and this is our first derivative test that's telling us this. So if I look at the graph of this, okay, this is what's going on. Here is that point. Remember that was x equals -1, which is right about here, where my derivative is 0. And you can see that it kind of flattens out there. The derivative is 0, but it's neither a local minimum or maximum. It just kind of levels out and then continues going up. And so that's the case where your critical point says it's a candidate for being a local minimum or maximum, but since you don't have a sign change from one side to the other of the critical max, or the critical value, you neither have a minimum or maximum. The other ones correspond to exactly what you would expect. You have a local max, where you go from a positive slope to a negative slope, and you have a local minimum, where you go from a negative slope to a positive slope. Okay, so those are the words of what I said. Okay, so now we've talked about concavity before. We actually call this the concavity test. We've seen it before. The difference here when I'm asking you to do things and do these tests is I'm not going to give you the derivative. You have to decide, if I say what's the concavity, you're going to have to decide that, oh, I take the second derivative to find concavity. All right, so here, if the second derivative is positive over an interval, that means the graph is concave upward on I. If its second derivative is less than 0 for all x on I, then the graph of x is concave downward. Okay. And then if the second derivative is 0, what does that mean? Before it writes it. Oh, inflection point, right? Now your book doesn't call out C as being part of the concavity test, but you're bound to come along a case where the second derivative equals 0, and so if you're trying to do the concavity test, if you get 0, that means it's an inflection point. That means it's changing on one side from concave up to concave down or vice versa. And we use the same procedure as we did with the derivative in finding whether it's positive or negative. You know, we do this thing of factoring, and then we decide where it's positive and negative, and then we use that as a description for the original function, not of the derivative or the second derivative, right? So we're using the derivatives to characterize the main function. So when I'm asking about concavity, I'm asking about concavity of the function, but you're using the second derivative to make that decision. Okay, so now here we have the second derivative test. Now this is ambiguous, because what does this mean? Is it the second derivative as in f double prime, or is this the second as opposed to the first derivative test, which wasn't really the first derivative, that was the first in the order that we're talking about. So the second derivative test actually uses the, well, let me just lay it out. So let's suppose the second derivative is continuous near C. Okay? If the first derivative is 0 and the second derivative is greater than 0, then f has a local minimum at C. So it uses both the first and the second derivative. So when I'm referring to the second derivative test, I'm talking about this being as the other derivative test. All right? So we're using both the first and the second derivative. And when the first derivative is 0, what we do is we look for a sign change from f prime to tell us on the first derivative test if we're at a local min or maximum. This thing tells us if we take the second derivative and see whether that's positive or negative, it'll tell us if it's a local minimum or maximum. Now, from a practical standpoint, oftentimes, especially with a polynomial, it's easier to take the second derivative, plug in a value to see where you're positive or negative, rather than going through a whole table of values like this. So there is some economy to doing the second derivative test. So if I look at my, my function that I had before, I took my derivative, I found my critical values. I'm also going to find my second derivative, which right now should be kind of automatic to you since it's a polynomial. My critical values that I found before were were these three, and so all I have to do is plug those numbers in, and it tells me what I got. Okay, so if f double prime at c, when I plug in a -1, I get a 0, so I know this is not a minimum or maximum. If I plug in a 0, then I end up with -2, so I have a local maximum. And if I plug in a 2 to my second derivative, then I have a local minimum. So all that business that I went through with this chart to figure out is the first derivative positive or negative, the second derivative tells me just by plugging in a number. So it's a decision. Sometimes you get the second derivative or the first derivative. The second derivative is kind of a pain in the neck to get, so you use this kind of analysis. If you can take the second derivative in an easy fashion, then bingo, you're home clear. So there's really not a clear choice whether to use the first or the second derivative test. In some cases, especially when you have polynomials, the second derivative test is easier and it's faster. Okay, so, and I apologize for really speeding this up because I had some difficulty getting the Apple AirPlay going. But anyway, this is what your homework's going to look like over the weekend. It's going to be that old problem 6 from the last test about finding where it's increasing, where it's decreasing, intervals of concavity and things like that. So I will have this one worked out, and then you'll probably have 4 or 5 of these to do as your homework. And I'd like you to bring those in, in a written form on Monday. So I'm not going to assign it on web work because there is, there's a lot of kind of calculation involved here.
Thank you.
Okay? And let's see.
Do you want our
I
worksheet
guess I
back?
said, yeah. Please put your worksheet up here.